Algebra 2 Cram, New York State Algebra 2 Regents, Common Core, Basic Graphs of Trigonometric Functions, the domain of the cosecant of x. The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. Inbox me at memedicine@gmail.com to order this complete cram session. Be sure to spread the word to your friends and classmates who also need to cram. They too can inbox me at memedicine@gmail.com for pricing and ordering instructions. All right, let's cram through the domain of the cosecant of x. Basic graphs of trigonometric functions. Domain of cosecant x. Before we cram through this, let me orient you a little bit. I want you to recall exactly what the cosecant of some particular angle x is. And here, since we're going to use x to represent our x coordinate, we're going to say that the theta is the name of the angle rather than x, because we don't want to double up on variables. Here we see our x, y Cartesian coordinate plane, and we have an acute angle whose vertex is at the origin. The initial side ray is on the positive x-axis, and the terminal side ray ends within quadrant 1. Hence, it's an acute angle because it's bound by 0 degrees and 90 degrees. Okay, so any angle bound by the quadrantal angles 0 degrees and 90 degrees is going to be an acute angle. Okay. And we see that if we resolve this ray into its x-coordinate and y-coordinate, we have the formation of a right triangle. Okay, thus the cosecant of this angle theta is going to be r over y, where r is the magnitude of the terminal side ray. Note I said magnitude, so this is going to be a distance measurement, so it's always going to be positive, divided by the y-coordinate, or the side opposite the angle of interest, okay? And since this is a fraction, you have to take note and be careful when y is equivalent to 0, because that means the fraction is going to be undefined. And because this is an acute angle with the vertex at on the positive x-axis and the terminal side within quadrant 1, it's also a reference angle, which means that if we were to do, let's say, a vertical flip into quadrant 2, that means that you would have something that looks like this. And excuse my squiggly lines. It's the thought that counts. So let's say this acute angle theta is like 40 degrees. Well, over here, you're not looking at 40 degrees. What you're actually looking at is this. So if you were to calculate the cosecant of theta in quadrant 2, you would actually be wanting to calculate the cosecant of 180 degrees minus 40 degrees, which is going to be the cosecant of 140 degrees. But it's going to be actually no, it's going to be positive. But I just want you to note that when you switch from quadrant to quadrant, although you might have a reference angle that your calculator is calculating the trigonometric value for, you have to be careful of the sign and also the value of that particular angle. So using the reference angle example, if you were to do a diagonal flip into quadrant 3 over here, what you would actually be looking at is an angle measurement of 180 degrees plus the reference angle theta ref. We can call it theta reference. And as for quadrant 4, what you would want to do is look for the angle value by subtracting the theta reference from 360 degrees. I hope all of this doesn't confuse you. And if it does, I'm really sorry, but the more you get into this, the more you'll understand what I'm talking about. I just want to point out some major concepts to you, okay? And so again, the y value or the opposite side and even the x value can be negative or positive depending on which quadrant you're located in, okay? All right, and note that the cosecant of theta is the reciprocal of the sine of theta, which is basically going to be y over r, okay? So the sine is equal to y, the y coordinate, over r. That means if you were to multiply the sine of a particular angle by its cosecant, you'd get 1, okay? All right, so that's that. Now let's get into the actual concept or question. What is the range? I mean, and not the range, domain. And when I say domain, what I mean is the set of all possible independent variables. The independent variables are the input variables, or the x values, the values along the horizontal axis of the function y is equal to the cosecant of x. I'll give you a moment to think. What is the domain of the function y is equal to the cosecant of x? All right, so hopefully by now you were able to arrive at an answer, and if not, that's completely fine, okay? Because we're going to go through this together really quickly. So here goes an awesome depiction of y equals the cosecant of x. And notice it has these weird interruptions. Okay, and that means that the domain is all real numbers except for multiples of pi. And remember what I was pointing out to you earlier is that at multiples of pi, like 0, 1 pi, 2 pi, okay, you have no y coordinate. It's like a decrease all the way to flat. So therefore it's going to be 0. But even if this weren't a right triangle in a Cartesian coordinate, you know, you can still calculate a cosecant value. It's just that for these particular angles, the cosecant is 0. So you get vertical asymptotes there, but in between these multiples of pi, you have the function cosecant traveling either upwards in the positive infinity direction or concave downwards forever in the negative infinity direction, okay? So you have these alternating concave up and concave down curves. So again, the domain is going to be all real numbers except multiples of pi. And just in case you don't know what a real number is, real numbers include integers, rational numbers, and irrational numbers. When I say integers, I mean numbers like 0. Well, that's like a really flat 0, like -1 and 2. The counting numbers along the number line is like the best way to define an integer. And also, it includes rational numbers. Rational numbers are numbers that can be expressed as fractions a over b, where b is not equal to 0, but b can equal 1. For example, 2 over 1, 2/3. Okay, and what you need to know is that when you convert a rational fraction into a decimal, it either terminates or it repeats. 2/3 is 0.66, and 2 over 1 is 2.0, or 1 over 2 would be 0.5. These are all rational numbers. But an irrational number can't be expressed as a fraction a over b. At least if you try to, it's going to be nonsensical. And an example of an irrational number is going to be the square root of 2 over 1, we'll say. And the reason why this can't be an irrational number is, first of all, when you try to evaluate the square root of 2, you wind up with a number that has a non-repeating eternal decimal, okay? So it's going to be something like see, it's 1 point. Sorry for the lag in my writing. That's supposed to be a decimal point. 4, 1, 4, 2, 1, 3, 5, 6. I'm not going to write out all the digits because it's taking up way too much time because my tool here is a little janky. But yeah, so this cannot be expressed as a non-repeating decimal because if you were to look at all the values after the decimal point, it continues on forever. Okay, so again, real numbers are rational and irrational numbers, and the integers are included in rational numbers. Okay. All right. So yeah, here goes the range, not the range. I mean the domain of the cosecant of x. Thanks.